In this lecture, I'm going to give you an outline for the rest of this course. First, I want to give you a brief summary of what PyTorch is all about, in case you've had previous experience with TensorFlow or other deep learning libraries such as Theano. So in the beginning, there was Theano. Theano was a significant improvement over what was being done previously for two major reasons. Number one, for reasons you'll learn about later, writing neural networks from scratch involves doing a lot of matrix calculus by hand and then copying those equations into code. For those of you who took my first deep learning course, you know how difficult this can be. The Theano library was the first to innovate in this area using automatic differentiation, or autodiff for short. What that means is you don't have to write down calculus equations, since the computer will do that for you. And number two, there's a lot of math that has to happen in a neural network, and this takes a lot of time, meaning you'd have to wait hours or even days or weeks to train your neural network. The Theano library was the first to innovate in this area by making use of GPUs, which were originally designed to improve the performance of PC games. One of the downsides of older libraries such as Theano is that you have to build everything by yourself. This can really slow you down, especially if it's your first time writing certain components. You'll not only have to write each component on your own, you'll also have to worry about them being right. If any single component you wrote is wrong, then it could make your entire program fail. On top of that, in the previous years, it was announced that the Theano library would no longer be maintained. What about TensorFlow? TensorFlow is a pretty popular library, thanks to the fact that it's backed by Google, who at this point kind of run the internet. TensorFlow used to be really messy, in fact probably more so than Theano, but now in version 2.0, it uses the Keras API, which is the total opposite. It's very high level and very simple. But there is a downside to very high level and very simple APIs. They make it very easy to do common things, but hard to do uncommon things. PyTorch, on the other hand, has been slowly gaining adoption in the field of deep learning, thanks to the fact that it's relatively easy to do common things and still easy to do uncommon things. For this reason, it's been extremely popular in the research community, who, by definition, do lots of uncommon things. That's their job after all. PyTorch is developed mainly by another internet giant, Facebook, specifically the Facebook AI Research Lab. As with all deep learning libraries, PyTorch is supported by GPU acceleration and has automatic differentiation, so there's no need in this course to use tools like calculus and linear algebra to derive backpropagation. If you hate math, then you should feel very lucky. In fact, we won't discuss backpropagation at all, despite the fact that it's really the main ingredient that makes everything work. This, combined with the fact that a lot of the basic building blocks are already built for you, are some of the major advantages, which are going to allow us to blast through each section very quickly. In the past, it was necessary to focus on each architecture one at a time, with RNNs being the most complex to implement. These days, ANNs, CNNs, and RNNs can be implemented in just a few lines of code. Alright, so how is this course structured? First, before we even begin discussing deep learning or any type of statistical modeling, we are going to look at a new coding environment which I really like, called Google Colab. Google Colab is basically Jupyter Notebook hosted by Google, but with a lot more bells and whistles. Personally, I have never been a fan of Jupyter Notebook, since it seemed to have more disadvantages than advantages. However, Google Colab is a different beast. It's hosted by Google, so you don't have to use your own computing resources. It's free, so it doesn't matter if you have a slow computer or a fast computer, everyone has the same access. It gives you free access to the GPU and TPU for orders of magnitude faster training and inference. And finally, most of what we need is already installed, so you don't have to waste any time installing libraries yourself. Once you've done that, we are going to go through the fundamental architectures involved in deep learning. Believe it or not, this all starts with linear regression, the line of best fit you learned about in high school physics. We'll see that with just one little change, adding the logistic function on top of a linear model, we will get a neuron. This covers the two major types of supervised learning, classification and regression. Once you know the basics, it's time to get started with deep learning. The first deep learning architecture you'll learn about is the artificial neural network, also known these days as the deep neural network. Although neither of these names really do a good job of differentiating it with other architectures. Next, we'll dive into image processing with convolutional neural networks. You'll learn about convolution and how this works to create neural networks that are specially designed to achieve better performance on images and other physical signals. Next, you'll learn about recurrent neural networks, which specialize at working with sequence data. Unlike my previous courses, where we used RNNs mostly for natural language processing, we are going to start with time series forecasting. This is going to let us cover a lot of ground that many other courses simply skip over entirely. In particular, we're going to cover the difference between the wrong way to do a time series forecast and the right way. We're going to look at several time series that simple models like linear regression can and can't solve, as well as several time series that slightly more complex models like the simple RNN can and can't solve. For the more difficult problems, we'll see how the LSTM achieves superior performance. And so, you'll see firsthand why LSTMs are useful, rather than me just telling you and you accepting it as fact without observing it for yourself. The next example is one of my favorites in the course, which is on stock prediction with LSTMs and RNNs. I think most of you will find the contents of these lectures very surprising. If you've ever learned about stock prediction with LSTMs in the past, be warned. Most other instructors are doing this the wrong way. In this course, I'm going to teach you why it's wrong, how to correct it, and what some of the real obstacles are in stock prediction. The first major part of this course is about the fundamental architectures in deep learning, while the second major part of this course is focused on applications. As a side note, if you want to just skip the rest of this lecture and move on with the rest of the course, that's fine too. The first application we will look at is natural language processing, specifically with text documents. You'll see how we can use deep learning for text classification, which is the type of task you would use for spam detection, sentiment analysis, and so on. We'll also look at embeddings, which are deep learning's method of dealing with categorical data. Embeddings will lead us to our next application on recommender systems. Now, it might seem weird to think that natural language processing would be somehow related to recommender systems, but hopefully in this course you will learn about the hidden connection between these two different fields. Recommender systems is all about how to optimize the products or items that you recommend to your users. Facebook, Amazon, and Google have been using recommender systems to improve their profits by the billions. When you go to Amazon.com, it is full of recommended products for you. Facebook's newsfeed and your Instagram feed are both recommendation lists. Google's search results, advertisements, and the YouTube sidebar are all examples of how Google uses recommendations. In short, recommender systems are one of the most practical business applications of deep learning, and one that can be used in a pretty straightforward manner to improve your profits. This is in contrast to, say, natural language, where it's not exactly clear how that would directly tie into how much money your business makes. Although, it's already a fundamental part of our day-to-day lives, so don't discount it just yet. The next application we'll discuss was a game changer for deep learning. If you've taken any of my deep learning courses in the past, you know that training a deep neural network takes time, lots of time. You might end up waiting hours or even days or possibly even weeks. Luckily, machine learning engineers have found new ways of allowing us to build on top of the work of others. The idea is, companies like Google or Facebook or university research groups will train large neural networks on humongous datasets, such as ImageNet, which contains over 1 million images. That's not the kind of thing you can feasibly do on your home computer. Using transfer learning, what we can do is take just a part of their neural network and combine it with our own neural network designed for a specific task that we want to do. Results have shown that this is an easy, and more importantly fast method of building state-of-the-art deep learning models. In just a few seconds, you can integrate the power of bleeding-edge neural networks into your own applications. Next we have GANs, or Generative Adversarial Networks. This was named as the most interesting invention in machine learning in the past 10 years by Yann LeCun, a deep learning pioneer who is now the chief AI scientist at Facebook. GANs are all about generating images using a system of two neural networks. One that generates the images, and one whose job it is to discriminate between real and fake images. Using this pair of neural networks, they both help each other improve. So the discriminator becomes better and better at recognizing fakes, while the generator becomes better and better at creating realistic images that cannot be differentiated from fakes. When people think about deep learning, they don't often think about how neural networks can be used to generate things, but rather just how neural networks can make predictions on things. Predictions are nice, but generating things opens up a whole new world. Recently, Google announced a conversational AI, where you could have a personal assistant do something like call a restaurant and make a reservation for you. But that personal assistant is not a person, it is a robot. All of its speech is generated by a computer. Another exciting application of deep learning is in reinforcement learning. Usually, deep learning is used to create models with a static input and output. For example, you put in an image and it tells you what this image is of, like a car or a truck. Or you put in an email and your neural network tells you if it's spam or not spam. But some tasks require multiple steps, which requires having some long-term strategy and keeping track of state. For example, if you're playing a game like Super Mario, you can't just look at a still image of the game and decide what to do. Instead, you need to have a long-term strategy. You have to know that you should walk forward to reach the flag for that level. You have to know that if an enemy is walking towards you, you have to avoid it or attack it. And also, you have to have proper timing in doing so. This is what reinforcement learning is all about. To summarize, the outline of the course is like this. We can split it into two parts. Part 1, architectures, and Part 2, applications. In Part 1, we discuss the fundamental architectures such as linear models, ANNs, CNNs, and RNNs. In Part 2, we discuss applications such as NLP, recommender systems, GANs, transfer learning, reinforcement learning, and possibly more. Thanks for listening, and I'll see you in the next lecture.